Okay, welcome back, everyone. I hope everyone is fully caffeinated and ready to switch topics into machine learning through the lens of physics. Uh, Yesterday was really fun to give the public talk and give you kind of a cartoon view of some of the things I've been thinking about, show you some pretty pictures. Today we're going to roll up our sleeves and get to some equations behind what machine learning is, at least through this kind of physics language. So just to remind you what we did last time, I mentioned that kind of the paradigm that we're going to be thinking about machine learning is that of simulation-based inference, or SBI, where we assume that we have access to the probability of some data set given assumptions about the model. So I take the standard model parameters, I can simulate synthetic data that's coming from, for example, a collider or some other experiment. And given a model that I can simulate to get data, that's, of course, synthetic data, I then want to look at real experimental data and infer what the underlying parameters are. So that's the rough paradigm that we're thinking about for simulation-based inference. And a couple things that we're going to use, since I come from the collider physics community, when I think about a monstrous data set like that coming from a collider, where if I really imagine all the possible collision events that could happen, n collision events, where n can be very, very large, that is a very large type of data set to try to imagine manipulating. But luckily, each collision event at the LHC is independent and identically distributed. That is, one collision doesn't affect the other one, and each collision basically has the same properties, up to some subtleties that are fun to discuss on the experimental side. But at least from a fundamental physics perspective, the collisions are independent and identically distributed, otherwise known as IID. And so actually, if I understand the probability for one phase space configuration, that's sufficient. And we'll use that simplification, and the simplification is also relevant for other data sets that you might encounter. And then just as a kind of an advocacy level, I'm advocating for the Centaur science. That was, of course, what the public talk yesterday was talking about. But finding ways of balancing our physics knowledge and these machine learning techniques. And part of balancing physics knowledge and machine learning techniques is to try to engage with machine learning strategies using a physics language so that you'd be more familiar about how you might actually use them. Okay, so let me just pause here and see if there was any questions about last time before I go into the lecture today. Okay. So machine learning has this annoying reputation of giving black box uninterpretable solutions. And in my view, that kind of profoundly misunderstands what machine learning is and what its goals are. In my view, interpretability and understanding comes in the way we frame problems, not the solutions. When I do some kind of Feynman diagram calculation, I don't expect that the answer that I get is going to be something that's easy to interpret. Certainly certain features of it, as Nathaniel showed before, we can interpret maybe in some higher level language, but the actual results of doing a calculation are not necessarily interpretable. It's the framework that we use to set up the problem, that's the thing that we have control over. And that's also the kind of the way that I think about machine learning, that we get to establish the problem that we want to solve, and then it's up to us whether or not we've defined the problem in such a way that the answer is satisfying. So I'll show you some examples here about kind of ways of baking in elements of interpretability into neural networks. But more, I want to show you how some of the ideas from machine learning are very natural from the physics perspective. And I had a colleague at MIT who basically said something to me along the lines of, wait, that's all machine learning is? And the answer is yes. At some basic level, it's going to be as simple as what I show. Though actually there's a huge range of algorithms and applications that, of course, go beyond these basics. But I really want to make sure that I cement the basics in your brain. And again, remarkably, some of the absolutely eye-popping results in AI, they come from these basic foundations. So that's why I want to emphasize them in these lectures. So we're going to talk about machine learning through the lens of physics. And there are going to be 4 ingredients that I'm going to explain to you and translate as best that I can into a physics language. Just at the slogan level, I'm bringing the slogan up here. Remember, machine learning is optimization in response to data. So number 1 is data. So what is the data that I'm using to train my machine learning algorithm? I better have an objective, otherwise known as a loss function, that I'm trying to optimize. So I have to define that objective. I need to have a thing that I'm manipulating, something whose knobs I can turn in order to get a desired solution. So that's a learnable function. That is a function that's flexible enough to respond to the optimization procedure, and then the optimization algorithm itself. And each of these ingredients we could spend a lot of time on. I am going to focus a lot on this, the objective, just with the idea that you get to define the problem you want to solve, and therefore you need to choose the objective that you want to use. I'll spend less time talking about these other elements, though they are also quite important for actually doing machine learning in practice. Okay, and then all these things connect to physics ideas in some way or another. So if I start with training data, I've already kind of emphasized this fact that the data itself really comes in this form of the probability of some data set coming from some model. That is, data is probabilistic. And so whether you're looking at real experimental data, simulated data, or whatnot, you're imagining that you have some probability distribution that you're drawing from, some probability of your data given some source. And of course, that source could be a natural source. You could take photographic images of the world and say that I'm drawing from the probability distribution of photographs. Or it could be data collected from an experiment, or it could be equations coming from a theory calculation. But there's some notion of a source. And the reason why I want to emphasize that it's probabilistic is that there's very rarely cases where you have all of the data, all of the examples that you could have. You can't see all the possible photographs of cats. You can only see a selected subset on your Instafeed. So the other thing to emphasize, and this is going to be important, and just kind of tying back to physics, is that if I'm thinking about having a probability in the case of, let's say, particle physics, probability over phase space coming from some model, let's say the standard model, usually I don't care about this probability distribution directly. Usually when I'm doing quantum physics or statistical physics, we typically care about expectation values or means. So, even though this is in some sense kind of the full information, we usually do some type of summary. And a typical summary is to take an expectation value. So for example, if I have some probability distribution P, so I'm going to take an expectation value over P of some function of my phase space point. This is defined as the integral over all possible configurations of the probability and then this function that I'm trying to take the average over. This is the typical type of information that we typically like to process. So for example, if I'm taking data and putting them into histograms, I'm taking a function f that selects only those data points that correspond to that histogram bin, and then I'm computing the average occupancy of that histogram bin. So that's a typical thing that we do. Okay, so we now have this kind of tension, if you'd like, a tension that is very familiar in a physics context, where the kind of fundamental object that I have is continuous, and when I'm defining this as an integral, but when I'm actually getting data, data itself is discrete. And so this came up a little bit yesterday, of this difference between discrete and continuum. But anyone who's done practical theory calculations knows that you can get really good estimates of integrals if you do phase space sampling or Monte Carlo integration. So if you only have finite samples, then if you want to estimate the expectation value of some quantity, then you approximate it by taking a bunch of examples labeled by I, let's say n examples. You compute the function on each of those values of I, and then you weight it by 1 over n. So this thing here, these are samples coming from P. And I don't have to do the full integral. Just with stochastic samples, I can get a good estimate of this expectation value. And this is just Monte Carlo integration, like a complete workhorse of particle physics and other fields for that matter. Is just saying if I want to do a high dimensional integral with samples, I can estimate it reliably. And I have this in my notes, but I'm not going to go through it here. And happy to talk about it if you're interested in. The uncertainty in this procedure scales like 1 over the square root of n. So if you make n bigger and bigger and bigger, your estimate is more and more accurate in a way that scales like 1 over the square root of n. So when I'm choosing a training data set, so if I now think about what does this have to do with machine learning training data, like literally machine learning training data is just samples. These samples are coming from presumably some underlying probability distribution. And the more samples that I have, the more accurate I am at estimating integrals. So all training data is samples from a probability distribution and if you want to know how much data do you need for your problem, roughly speaking, you need to know, well, what accuracy do I need to have to make a good decision? Now, we often don't think about our data in this way. Oftentimes we think about, like the examples I gave before, you know, all the cat photos on your social media account. You don't usually think about that as coming from an underlying distribution of cat photos, of which I have a stochastic sampling of them. And in fact, probably in applications in society, like we really don't think about, there's a probability distribution over all possible word sequences, and what's in a library is just a stochastic sampling from that. I'm stochastically sampling books. We don't usually think about our information that way. And indeed, it seems a little bit awkward when you're thinking about it for textual data or image or video data. But in the context of physics, and in particular particle physics, it's like literally exactly true that we have an underlying quantum probability distribution, and that is what the data that we're trying to collect is, and it really is, we believe, we have no control over selecting what data nature is going to give to us, stochastically sampled from that underlying physics distribution. So that's training data, that's it. Any questions? Yes? Yeah. This, if you're familiar with Monte Carlo integration, these are what's called unweighted samples. So unweighted samples, each event comes with equal probability. So when you're given a stack of photographs, you take those photographs and you treat each of them as having unit weight. But what you point out, which we'll come to in a little bit, is that wait, why not just treat them in a weighted way? For example, let's say I want to generate more data, I want to be more accurate in a particular region of phase space. I can generate more examples in that region of phase space to make it more accurate, and then just put appropriate weight factors. So I could put, if I wanted to, I could put weights in here, and this would correspond to doing weighted Monte Carlo integration. So you can absolutely do that. In fact, it's useful to do that, and we'll do an example of showing that appearing. But when you hear people talk about machine learning training data, they usually talk about unweighted samples. And we can use our physics knowledge to say, well, actually, maybe you can do a better job if you weight things. And an embarrassingly large number of my own papers have come from just adding weight factors like you just described. Okay. Okay, that one was easy. The next is about an objective function, or objective, otherwise known as a loss. So what is the language? So sorry, I should have said training data is connected to Monte Carlo integration. So that's like the physics translation of what training data is. It's just Monte Carlo integration. So what is objective functions in the language of physics? Objective functions is just Lagrangian mechanics. And the fact that loss functions and Lagrangians have the same L at the beginning is a hint that they're connected. That was supposed to be a joke. Is it like, really? Okay, no, not enough coffee. So let's do a classic example of pre-AI, like just really basic machine learning of a classic problem that I want to show you is just Lagrangian mechanics in more than one dimension. Okay, so we're going to do regression. More generally, nonlinear regression. And for regression problems, you're given a sequence of XY pairs. And what you're trying to do is saying, if someone gives you a new value of X, you want to predict what Y is. So, you know, I give you, I don't know, well, the example I did last night as part of the public lecture is I was giving you data that's a bunch of jets, and I wanted to give you a label about whether it's a quark or a gluon. So I give you a bunch of examples of example jets and what their quark-gluon label might be. And I can imagine treating that as a regression problem of predicting some kind of probability or estimate of whether it was a quark or a gluon in some kind of fractional way. So I can imagine doing a regression task. Typically, we actually do that as classification, but let's just imagine that this is my data set and I want to do regression for it. So what is the loss function associated with regression? So what you do up to some weight of, so there's n examples here. What you're told to do for standard regression is sum over I from 1 to n of saying, I would like to learn a function f that ingests x and spits out y. And if the loss function is 0, then I have a function that perfectly can say for an x that I give you, it will perfectly tell you what the y value would be. More generally, because of noise or the structure of the problem, you're going to get a loss that can't get quite to 0, but you'll do a good job on average of saying, given an x value, what is the y prediction. Okay, but based on what I have up here, every time you see a sum over I from 1 to n, you should say, oh, that's just an integral. That is, even regression can be gone into the so-called asymptotic limit, and I can think about it as if it were an integral. Of course, in real life, we really are using that sampled data, but if we think about it as an integral, we can at least understand what would happen if I had infinite training data, and that can help us understand the behavior of the machine learning system that I'm building. So, in this case, the approximation is going the other way. Now the loss here, this is the sampled loss. The sampled loss is well approximated by an integral. And what's my data type? My data type are xy pairs. Therefore, I have an integral over x and an integral over y. I have a probability distribution that I imagine sampling these xy pairs from. So I have a probability of x and y. And then I have this quantity that's in my loss, the thing that I'm taking the average of. And so that's just f of x minus y. And now I'm supposed to optimize this. And imagine I could do perfect optimization of this quantity. So if I do perfect optimization, how would I go about doing it? And to use the physics jargon, we would solve the Euler-Lagrange equations. Right? That's a very strange-looking Lagrangian. There's no derivatives on it, so it's just a Lagrangian that involves just coordinates. So it's actually quite simple. And so with the Euler-Lagrange of this particular case, because there's no derivatives, is somewhat trivial. So in general, if I have a Lagrangian that's a function of some Lagrange density, or if an action that's a function of Lagrange density, then the solution, the minimum, or the extremum, is when the functional variation of script L with respect to f is equal to 0. And this is the Euler-Lagrange if there's no derivatives. So again, it's quite simple. So we're just going back to, our classical mechanics. And in this particular case, that example of regression is pretty straightforward. So if I were to do, so for the case of regression, if I were to do the functional variation with respect to that function f. So I'm imagining right now that f is infinitely flexible. And if f is infinitely flexible, then I can imagine doing Euler-Lagrange style manipulations, and I want to set that equal to 0. So taking that top expression and doing derivatives, hopefully I can do this in my head, or at least I have the notes to help me. So f is only a function of x. So that means the y needs to stay there, so I still have my integral over y that's persisting. P of xy, that's still there. And then the derivative of what's on the inside there is just f of x minus y. So all I'm doing is taking a derivative with respect to f and just being careful that I also have this y dependence here. And then setting it equal to 0, what does this give you? Well, it gives you a solution for what f of x is. So even though f of x looks like it's inside of this integral over y, we can pull it out because there's obviously no x dependence in the integral. And so I can just rearrange this to solve. And so f of x is equal to the integral dy of p of x comma y times y divided by the integral dy of p of xy. And so what is this? Well, I pick a value of x, and then I take the average value of y that's in the numerator, divided by a normalization factor. So this literally is just average of y for fixed x. So when you're doing a regression problem, that's all you're doing. When you're doing a regression problem, you're taking sampled data, and you're trying to find the expectation value of y conditioned on the input x. So if all your data has the same value xy pairing, then you'll just get the unique answer. If there's variability, if the y values are different, even for the same input x, if there's some noise, then the thing you'll get is the average. Is this what you want to solve your problem? If your physics problem, if this is what you want, then great, congratulations, you've succeeded. If not, please do not use this loss. Right? And I've had fascinating conversations with people that said, oh, I turned my problem into a regression problem, I solved a regression problem, and I asked them, is what you actually want to get the average value of some quantity conditioned on your input? And they say, no, I'm not doing that, I'm doing a regression problem. It's like, no, do you want the average value of your output for a fixed input? No, I'm doing a more fancy regression. It's like, no, you're not doing more fancy regression. Like, the definition of the regression problem is exactly that. And if that's not what you're looking for from your algorithm, then please don't do it. And indeed, if I'm trying to do frequentist inference, do not do this, because this is not frequentist inference. Okay. We'll do that next time, how to do frequentist inference with this. Now, of course, if you have finite training data, imperfect optimizers, you won't get exactly this answer. There's various uncertainties, one uncertainty from sampling, one uncertainty associated with the optimization, uncertainties associated with how flexible your f is. But at least asymptotically, that's the thing you're trying to achieve with this. And so when we say we're using this particular loss function, that's what we're trying to guarantee the end user. As we're saying, roughly speaking, you're going to get this, this averaging procedure. Okay? So let me give you homework, which some of you may want to do right now. Which is kind of one of the simplest examples that you can do beyond regression, which I will also give you an example from, but I'll motivate it from a more physicsy perspective. But this is the homework with the following question. So imagine that you don't have just one data set, but you have two data sets. So I have two data sets. One data set is drawn from distribution P, and the other one is drawn from distribution Q. And in each case, I have samples drawn from one distribution, samples drawn from the other. So given my lecture last night, this could be samples of jets coming from the quark category, samples of jets coming from the gluon category. And let's say I'm going to build a loss function. I'm trying to learn a function f. And here's what I'm going to do. I'm going to say that, okay, there's an overall minus sign for conventions, that I'm going to, well, sorry, P of base space phi. So this is, again, you should imagine every time you see integral of a probability distribution, this is the thing that's going to correspond to your sampling. And now there's going to be some function, it could be a polynomial, special functions, whatever, or some functional of f. And then a similar term involving q with some other function b of f. Okay, and your homework is to find as many A-B pairs such that the solution for what f is, that is the f that optimizes this, is interesting. And as I'll advocate, one thing that's useful is if I can find a ratio of the probability distribution of P divided by the probability distribution of Q. That is an interesting quantity. So if you succeed in doing this task, if you come up with a list, I think if you find something like 4 or 5 of them, then you've rediscovered basically all the classic loss functions in the machine learning literature. So you will be able to discover all the buzzwords: binary cross entropy, mean squared error, square root loss. But the one you won't be able to find probably is the one I'm going to show you in a second. But if when you hear about these loss functions, they have these funny words around them. All they are Lagrangians, whose Euler-Lagrange equation gives you a solution that corresponds to something like a ratio or ratio-like. That's the goal of those machine learning loss functions when you're given 2 data sets, and you can generalize this, of course, to have more than 2 data sets. Okay, it may not be obvious that this is a useful ratio to do, so I'll give you a motivation for why you might want to do it, and then give you an example of a loss function which we're going to use kind of a physicsy way of thinking to come up with precisely that kind of A and B. Okay, so we're going to do, we did regression already. So the other classic machine learning strategies that people talk about are classification and generation. So classification is what I stupidly said before. Classification is given a data set trying to say what category it's in, which is distinct from regression. And then generation is generating synthetic data that has a particular property, let's say mimicking some existing data set. But we're going to do baby generation. We're going to do this by what was mentioned before, by doing weighted Monte Carlo. Okay, and these are secretly the same problem. So let's say what I have, so I'm going to do it from the perspective of this baby generation, because this is like the context that often happens in physics. So let's say I have a Monte Carlo generator, but my Monte Carlo generator is for the wrong probability distribution. It's a Monte Carlo generator for Q. So what does that mean? That means I can compute the expectation value of any function with respect to Q. So I'm giving an estimate, well, sorry, the actual expectation value is just the integral over Q times F. But again, we're going to estimate this as samples. Now samples drawn from Q and samples coming from Q. So that's what I have. But what I want is not the expectation value with respect to Q, but the expectation value with respect to P. Okay, so I want to compute the expectation value of F, but with respect to a different probability distribution. Okay, so this is what I want. And this is a very typical kind of situation that you find yourself in physics. You have some computational resource. Someone might have done a really good job optimizing this Monte Carlo event generator, or Monte Carlo generator, but they're doing not quite the problem that you want, and you want to fix it up. So you want to go from this to this, But you don't want to have to rewrite your whole computational framework. So if I have this, but I want this, what do I actually do in order to get the desired quantity? And as I said already, this is related to weighted Monte Carlo event generation. Okay, so let's just manipulate the thing that I want. I want the expectation value with respect to p. And I'm just rewriting what I already had on the board already. And we do the time-ordered strategy in physics of multiplying by 1. So multiply by q over q. I haven't done anything yet. Oh, but wait, if I integrate over q, right, then that corresponds to taking an expectation value of something with respect to q. What is remaining? I have f times p of phi over q of phi. But what I was told is that I have a generator that can calculate this expectation value. But it's not just expectation value for a particular f, it's expectation for value for any f that I might hand it. So all I need to do is hand it this quantity, the original f times this weight factor. And if I have a loss function that estimates that weight factor, then I've built for me, out of a Q generator, I've built for me a P generator. So that's the reason why this particular function is interesting. When I have this particular function, I can now use it to compute properties of some different distribution given some original baseline. So I haven't yet told you how to get this ratio, but first let me just pause to see, do you agree that, okay, up to some statistical subtleties about whether this is, what the uncertainties are associated with it, which is a fun exercise to do offline, at least an expectation value, the expectation value will correspond to the desired quantity. So any questions about that? Okay, so let me draw it in pictures for you. So if I imagine doing this in one dimension, imagining phase space is simple and one-dimensional, I have the ability to generate, to make random samples according to a distribution Q. That's what the resource that I have is. And I can use that resource to randomly sample in terms of Q to estimate the integral of this times any function f. Then I want to actually do the integral with respect to p. And in general, that will give me something different. But if I can compute the ratio, or more generally, if I can compute, not more generally, for different visualization, the logarithm of the ratio of p over q, then, of course, there's a crossover point where the ratio is the same. So that would correspond to the logarithm being 0. And then I would have this, this function where if I'm having samples from my Q generator, which are down here, I have to upweight them. That is, I have to have weight greater than 1 in that region of phase space, and weight less than 1 in this region of phase space. And again, as long as these weights aren't kind of too big, that gives me the ability to build a weighted generator for the thing that I want. So again, we don't usually think about things this way, but let's say I have a distribution of cat images, and what I really want is a distribution of dog images. So what I can do is I can take the cat generator, we'll just spit out cat images or cat videos, and then I reweight that cat video generator by the probability that that particular image is coming from a dog divided by coming from a cat. Now you can think about, wait, how many videos are there that could be confused to have a reasonable weight of both being a dog video and a cat video? None whatsoever, right? Because that's a case where the confusion is small. Or similarly, the weights that I would have would be kind of like astronomically large. But in physics applications, we're often in a situation where actually the overlap of distributions is not so dissimilar. So if I give you a leading order event generator, and then I do a next to leading order weight calculation, the reweighting that I have to do from leading order to next to leading order is hopefully not so big. And so that this is the reason why this is actually a useful thing to have in a physics context, even though this kind of weighted generation is not so useful when I'm thinking about it for societal applications. So I claimed, again, I still haven't figured out how to get that ratio of P over Q. And I'm realizing I'm using multiple different definitions of F. So let me change this one. That really I want a weight function. And so the thing that I'm trying to learn here, I want this to be my weight function. So I have two different types of functions. I have functions that are the quantity of interest. And then there's the functions that correspond to some learnable function that will serve some purpose. In this case, I'm using it to reweight a generator. So I mentioned that classification and generation are very similar problems. So if I were to have this weight function, I can actually use this same weight function and build a classifier out of it. So how do I do that? So, sorry, up here, I want to have them on side-by-side slides. So this is how you use this ratio for generation or baby generation. And then if I wanted to instead do classification, I can build a classifier where I take that weight function and I just manipulate it a little bit. So weight divided by 1 plus weight. So how does this function work? So this function C goes to 0 if the weight goes to 0. And when does the weight go to 0? Sorry, I should have, let me rewrite what the weight is since I erased it. It's up there as well. So C goes to 0 if the weight goes to 0, and the weight goes to 0 if the probability for that thing happening under P is 0. So this is goes to 0 if the probability to see that configuration under Q is much bigger than the probability to see it under P. This is a function that goes to 1 if the reverse is true. So it goes to 1 if the weight goes to infinity. And the weight goes to infinity tells me that the denominator, this Q, blows up in my face. And so some people like to do this type of manipulation just to have a nice function C that goes between 0 and 1. So, so my function C will go from between 0 and 1. And now this is a thing that I can now take my samples from P and my samples from Q, and I can now plot their probability distribution, or to use a physics notation, I can plot their cross-section for that classifier. So again, C goes to 0 if Q is large. So if I have samples taken from Q, Q will end up being peaked towards 0. That's what it means to have a data set that has a certain property. It means that if I were to classify it with respect to another data set, it is more likely to yield a classifier value that's small compared to large. And the reverse is true for P. And so P and Q could be quark or gluon, P or Q could be signal and background. And so if you have access to this ratio, you can convert it to a classifier. And then once you've converted it to a classifier, let's imagine that Q is the standard model background and P is some new physics signal of interest. Then I can select values of my classifier that are large, and that would allow me to isolate events that are more likely to be, in this case, signal-like. So clearly having this ratio, if I could learn it, would be a really nice resource, and your homework is to come up with a loss function that does it. And in fact, there's something called the Neyman-Pearson lemma that says, at least asymptotically, if you had infinite training data, this is actually the best type of classifier that you're going to build. And actually, many tasks in fundamental physics can be achieved by manipulating things like this, including frequentist inference, which we'll do tomorrow. Okay, so let me just pause to see if there's questions about this. So if you're a machine learning expert, you would know what those loss functions would be. But if you're a physicist trying to gain an intuition about how you build loss functions, then you might go through the following exercise. And this following exercise is one that you can actually use to derive an interesting loss function that appears in the particle physics literature, but doesn't actually, to my knowledge, really appear anywhere else. And we find it useful as particle physicists. And I want to kind of show you how you do this derivation, thinking about it from a more physics perspective. So again, the problem that I have is that I am trying to, I'm trying to, with this reweighting, I'm trying to build a P generator. So I want a P generator. And what does that mean? That means that I have the probability of samples coming from P So this is someone gives me examples of, for example, background events or signal events. And what I would like to do is I would like to have a model, a machine learned model, that can, with high probability, generate the data that I'm seeing. So this is what it would mean to understand this data set. If you had a reliable model that could actually spit out things with high probability coming from the data set you're trying to mimic, then that would correspond to building a P generator. Now, eventually, we'll have this model be some kind of more fixed machine learned object. But if we imagine this thing being fully flexible, we can imagine trying to find the absolute most under the most optimistic circumstances. What would that model be that would generate the data of interest? And in particular, we want to find the absolute max, maximize over all possible models to with highest probability, get the data set of interest. Okay, so this is called maximum likelihood estimation. Okay, so what does that look like? Well, I want to mimic my whole data set, but as we said before, collider data is independent and identically distributed. So this probability over a bunch of examples splits up into individual probabilities. And what we typically do is take the logarithm to turn that into a sum. So we now have a sum over data points. This is now data points, again, samples from P. We have our logarithm, and then we're going to have the logarithm of this probability. So the logarithm for the probability of an individual phase space point given that model. And then it's annoying to deal with logarithms of dimensionful quantities. So let's have it divided by something that won't change the maximum. So it's not going to depend on the model that I'm trying to optimize, the probability of that same phase space point with respect to a reference model. Now I go to the asymptotic limit. I imagine I have infinite data. So now this sum over data points, I've now trained you that every time you see that, you should be thinking about, oh yes, that's really an integral. So this is n times, or approximately, n, sorry, there's still the maximum. So maximum over something that will have to go in this box, of n times the integral over all phase space points of the underlying true probability distribution P that I'm trying to build a generator for. And then I have a logarithm of the probability of the model that I'm trying to learn. So I'll call that P twiddle. That's the thing I'm trying to learn, and I would like for p twiddle to be close to p. And then divided by some reference model, which, maybe not surprisingly, I'll use because I'm imagining this weighted generation. I'll choose to just be this reference model. I'll just call it Q. So if I can succeed at maximizing over the most flexible p twiddle, to find the most flexible p twiddle that has the highest probability of mimicking the sample data that I have, then I would have succeeded at the mimicry task. Now, this doesn't necessarily look like a Lagrangian yet, but I will show you that it is, or a loss function. So if I want to convert this into a loss function, losses we typically minimize, whereas maximum likelihood estimation we maximize, so I need to flip signs. I'm going to call this whole object here, I'm going to call this the weight function that I'm trying to learn. So this is now my loss function, which is a functional of my W. Again, minus sign. I have my data that I'm trying to mimic, data to mimic, but now in the kind of continuum asymptotic limit. And then this piece here is the log of W. And now I want to optimize this quantity with respect to W. And I also drop this n because it's just a normalization factor. Okay, so can someone in their head tell me what the optimal value of W is to make this loss as small as possible? Would you say 1? Are you sure? So which is infinity? So if I make W bigger and bigger and bigger and bigger, the log of a bigger and bigger number is bigger and bigger and bigger. With a minus sign, it's smaller and smaller and smaller and smaller. Okay? So this is pathological. If you see a machine learning paper that writes this down, and they say, I'm doing the optimum over W to solve this loss, you'll say, it's unbounded. That's not a good idea. What really happens is behind the scenes, they're doing something that's keeping it bounded. But you'll see papers that write this down. But it better be a constraint. There better be some constraint that actually stops this thing from running away. There must be some physical restriction on the weights that make this actually loss function well defined. Can anyone think of a property of this is a tough question, so I'll be curious if anyone comes up with something. A property that this W has to satisfy in order to succeed. Like clearly, if I make W bigger, like that is that does not seem like the right answer to this problem. In particular, you can imagine what if you actually already had the right answer? What if your reference model was P itself? Then W would really want to be 1. It must be that somehow your answer depends on that reference in some way. Any ideas about what you might want to do? Yeah.
Maybe we have to normalize on all possible ideas we have on some sense.
Good. Well, see, so you said the right word, normalize. So you said normalize over all possible ideas of what a model might be.
Maybe choose a bunch of models and you say the sum of the possible weights.
Good. So you're imagining having an ensemble of models, and then saying from that ensemble, I want to, have some property. Here, we're just going to, at the end of the day, machine learning learn 1 function. So I don't get an ensemble here. I do have an ensemble of data points, but I only have 1 function. Yeah.
The integral of p twiddle is like a number somehow.
Yeah.
Like p twiddle of q can be from everywhere.
Good. Okay. So here, the insight is that the integral over p twiddle, if it were just, you said it was just a number, What number would you like it to be? 1. Then it would be normalized. Then not only would you have a maximum likelihood generating model, but like a properly normalized one. So that's a constraint, okay? Okay, but now I need to frame that constraint in terms of W. So I'm not changing anything. I'm just rewriting this integral now by saying this is the same as Q times W. So I haven't done anything. And remember, Q was my reference model. So if I have samples from P, samples from my reference model, I can use samples from my reference model to make sure that the integral over that reference sample, W, that's equal to 1. That's a constraint. And as theoretical physicists, if I want to impose a constraint, a hard constraint in a Lagrangian, what do I use? Lagrange multipliers. So now I have in here a Lagrange multiplier of integral d phi of q of phi w of phi. And that looks suspiciously similar to your homework assignment, with one annoying problem. I have a lambda here. Do you know what machine learning people call random coefficients that show up in loss functions? Or in algorithms in general? You know what they're called? They're called hyperparameters. But in this particular case, we know better. We know that actually this is a Lagrange multiplier. Therefore, this Lagrange multiplier should have, under the optimal solution, it should have a value. Okay, so more homework for you. Homework is to figure out, solve Euler-Lagrange equations. When you solve the Euler-Lagrange equations, you will find that the solution to this loss function has the following. So the solution has the following properties. It satisfies what you want. It satisfies that the weights, okay, really are asymptotically P over Q. And that you'll find that the value of the Lagrange multiplier is 1. And this particular loss function has a kind of goofy name. Well, actually, it has a couple of names depending on what coordinate system you use. So in the literature, it's sometimes called a new physics learning machine, which there's no obvious way why this has anything to do with new physics or learning machines or whatnot, but that's one language. Another language that you could call it is you could call it the maximum likelihood classifier loss. Because at the end of the day, this object can be used for classification and it's based on a maximum likelihood principle, but constrained to make sure that things are normalized. So we started off going through this perhaps painful statistical argument. At the end of the day, we just have this beautiful Lagrangian that has a kind of funny form. It has a logarithmic structure and a linear structure with 2 different data sets. But this is an example of the type of loss functions that you can build if you have some kind of principle that you would like to use. I should say that this is not a standard machine learning loss, but it's super convenient. And as additional part of your homework, and the reason why this also goes under this name of a new physics learning machine, is that the value at the minimum, so also part of your homework, the value at the minimum is related to something that has statistical meaning. So it's related to what's called the KL divergence, which we'll talk a little bit more about tomorrow, which at the value of the minimum is the integral over phase space of P log P over Q. This is a measure of similarity between two data sets, and that level of similarity between two data sets can be used as a quantity that you could try to assess whether, for example, you see new physics or not, which is why it has also the name of MPLM, with appropriate coordinate transformations. Okay, so I wanted to emphasize this thing, like you get to build loss functions with whatever properties. You can use the words, in this case maximum likelihood, turn that into equations. Those equations now turn into quantities that if I take those integrals and replace them with samples, now you're doing machine learning. And again, it's super concrete what you're doing. I'm not making any kind of random non-interpretable steps. Of course, I'm assuming that I have infinite training data. In reality, we have finite samples. But again, that's no different than when I'm doing Monte Carlo integration. Okay, any questions about this? So I call this a baby generator because I think reweighting Monte Carlo event generators, that's not usually what people think about as building a generator. And I'm going to use this example of what a real generator is as a transition point to the third topic of what you need to do machine learning. So a real generator is something where I have a map that takes some noise and then from that noise generates examples. So for example, if you've heard of diffusion model starts off with a noisy configuration and then out pops a photorealistic image. But my input is noise, my output is some desired quantity. Let's write that in equation form. So I'm going to be generating things. I'm generating stochastic examples. So I'm going to build a generator that's supposed to generate examples phi according to some underlying probability distribution. But what I'm going to do is I'm going to start by sampling noise. And I have a base distribution of noise. So for example, I can sample from some Gaussian, and that defines my noise. And now what I want is for a given noise thing, I would like to come up with a phase space point based on that noise. And written in equations, I would just turn this into a Dirac delta function if I'm using kind of the physics way of thinking. So I sample over my noise, and then I have a map that takes noise and gives me a phase space point, and that's the phase space point that corresponds to my distribution. So this is what a real generator is. And there are many different strategies to come up with a map that goes from noise to a phase space point. I mentioned diffusion models already. There are things called adversarial networks, generative adversarial networks, or GANs. A huge number of different generative strategies, but roughly speaking, they all kind of take this form. Now, this quantity here, that's not a fun integral to do in general. So if I look at this integral and I say, geez, I really want to do this integral, I need to figure out all the possible values of noise that give me a particular phase space point. That's really annoying to try to actually analytically do this integral. That is, even if I knew what the space distribution was, and even if I knew exactly what that phi tilde was, and even if I could somehow analytically do the integral over n, like, this would be annoying. But there is one case where it's a little bit less annoying. And it's a little bit less annoying if this map from noise to phase space is 1-to-1. Because if this map is 1-to-1, then doing that integral is not so bad. So if I let n twiddle of phi be the inverse of phi twiddle of n, then I can actually just do that integral exactly. Why? Because there's only one value of n for each value of phi and vice versa. And doing the integral over the Dirac delta function when there's only one value that hits is not so bad. So then I would have my p gen of phi is equal to what? Well, I need to have a Jacobian determinant. So now this is the Jacobian determinant of d phi twiddle with respect to n. Inverse, evaluated at n being the value corresponding to phi. So this is just my Jacobian determinant. And then I have the base distribution evaluated at the value of n twiddle corresponding to the phi point of interest. Okay. And so if you have a nice base distribution, actually more importantly, if you have a Jacobian determinant that's really easy to compute, then actually you can get analytic understanding. Even if this phi twiddle is a neural network, if you can compute this thing, you have to have an analytic understanding of the generated probability distributions. Now, not only do you need to have this object, you have to know what it is, but also it has to be efficiently, you need to be able to determine it efficiently. So for example, if phi is some really high dimensional phase space and n is some really high dimensional phase space, then you can have a very high dimensional by very high dimensional object that you have to take the determinant of, and that can be super painful. So you need to find ways to make this efficient. And I'm not going to talk about it in any detail, but there's a particular type of generative model called normalizing flows. And what normalizing flows are in this more kind of high-level language is they are functions phi twiddle of n that satisfy the property guaranteed that they're one-to-one. So that means they're a one-to-one map. That's a useful aspect of them. And they're objects for which this Jacobian determinant is computationally efficient to extract. That is, even if you're in a very high dimensional phase space, it's not computationally difficult to extract that object. And it's kind of a remarkable achievement to come up with a function that has those properties, guaranteed to be one-to-one, guaranteed to have a nice determinant structure. And that's why normalizing flows are popular, sometimes even for physics applications, because it's a special type of function that satisfies a desired property, and that desired property makes it useful for potential physics tasks of interest. So if you encounter in the literature someone saying the word normalizing flows, in your brain you say, oh yes, that's a nice way of building a generative model that's computationally efficient when I'm doing this integral over the Dirac delta function. So this is a nice pivot now to the third ingredient that we have for machine learning, which is learnable functions. But let me just pause here to see if there's any questions about that example. Okay. So the next ingredient I need for machine learning is I need to have some learnable function. That is, I need to have something that is close-ish to what Euler-Lagrange would want. So when I do the Euler-Lagrange equations for classical mechanics, I imagine that I can take my functions, or I can take my coordinates in that case, and I can make arbitrary variations of them to get whatever dynamics that I want. Numerically, you have to make choices. So for example, you could take a function and say it's a spline function. You know, if my trajectory is like this, classically, I could say, oh, I'm just going to approximate it as a bunch of linear components, and that would be, to some approximation, a good estimate of what that function would be. So the things that people talk about for learnable functions in the machine learning world is they talk about feed-forward neural networks, or maybe you've heard about transformers, or transformers are based on the attention mechanism, and these are all kind of buzzwords that correspond to just different choices of how you want to parameterize a function to be really flexible. So what's another flexible function parameterization? Like a Fourier transform. Can you use Fourier transforms in the context of machine learning? Of course you can. Like you can actually just have a linear basis of functions and learn the linear coefficients of a basis of functions, and then you'd be doing machine learning. As long as it's sufficiently flexible, as long as it gets closest to what this Euler-Lagrange equation optimal answer would be, then it could be potentially useful. And this learnable function is an opportunity to put in physics knowledge where you can impose constraints, like we talked about yesterday a little bit, like symmetries of the problem, such that that learnable function has baked into it certain properties that you desire. And the specific types of neural networks and whatnot have not actually found to be particularly interesting. That a bunch of different things seem to work pretty well for physics problems. Where you get a lot of benefit is if you actually have some knowledge that you can embed into your machine learning architecture that gives you flexible functions that aren't so flexible as to be hard to optimize, but sorry, are constrained enough to actually have the physics of interest, but not so constrained that they're hard to optimize. So let me give you the example that I showed you in the public lecture yesterday, where is when I showed that psychedelic image. And you might say, what possible like functional form would give me a psychedelic image like the one that I showed you? Okay, well, here's first the physics knowledge, and then what the functional form is. So the physics knowledge, which we talked about yesterday a little bit, is that identical particles are indistinguishable. And even if the particles are distinguished by some quantum number, the order in which you see particles is irrelevant. That is, nature doesn't know that this particle was created first, this particle was created second, this particle was created third, that the order of the particles doesn't matter. So from a phase space perspective, our phase space is an unordered list of 4 vectors, or 3 vectors if I assume that the particles are massless. So let's just imagine that these are momentum directions. And apologies for the overload use of the word P. Now P stands for particle, not for probability. And order doesn't matter. Okay. So therefore, if I'm trying to learn, for example, a weight function that I'm going to be used for classification, I would like to build a weight function that's invariant to permutations. So I would like this. If I ingest some particles, I would like for it to not care about the order. Okay, so here's a strategy for how you might do this. This is certainly not the unique strategy. In the machine learning literature, this is called the deep sets philosophy, because I have a set of information and I want to have a deep learning architecture that's invariant to permutations of that set. In particle physics, these are known as particle flow networks, which is a name that you can blame me for. Okay, so I want to have something that's permutation invariant. So what I'm going to start off with is I'm going to start off with a function little f that ingests particles, single particles, one at a time. I then sum over all the particles in my event that I'm trying to study. And already we see we're permutation invariant. Why? Because addition is permutation invariant. And then I have some bigger function, capital F, that encloses this. So little f is some function that takes me from, let's say, 3 momenta and maps me to some larger space L. This L stands for latent or hidden space, latent space. And then the capital F function takes me from that latent space and then gives me my answer. So if I'm doing classification or regression, or this weight function, it'd be some real number. Now, these two things I could parameterize in my favorite way. So I could parameterize these with neural networks if I wanted to, or I could parameterize these with Fourier basis or whatever choice that I want to make. But no matter what parameterization I use for little f and big F, because I have this summation structure inside this argument, I'm guaranteed to have the permutation symmetry. And so what I was showing in the public talk is all I was showing was plots of this function. I was showing you an attempt to represent what this function looks like. And even though I'm saying it's R3, what I did the talk was actually pull out specially energy as a special coordinate. So actually I made this just be R2 and put a little energy weighting factor out front. Okay, and then once you have a function of 2 dimensions that's going to L, then you can make a psychedelic image where you make a 2D plot, and then each L corresponds to Gaussians, or approximate Gaussians, of which the contours of that Gaussian is what I was showing on that crazy plot. And that's the way that you can visualize this particular neural network for reasonably sized L, just because the input dimension was small enough. So here I'm doing 2 things at the same time. I'm building in the physics knowledge of indistinguishability. If I were giving a QCD talk, I could tell you by this energy weighting here is related to the QCD concept of infrared and collinear safety. And then because I've broken up my neural network into kind of pieces here, pieces of like at least parts of this, I can actually try to visualize and try to understand what's happening. So that's an example, a very simple example of baking in physics knowledge into an architecture. So what if you say, wait a second, for the problem I'm interested in, I don't like this structure. I don't think that my problem is of that form. I think I can use additional physics knowledge to do a better job. Well, you don't have to use off-the-shelf machine learning. You can build a machine learning architecture that has whatever properties you want your network to have, either interpretability properties or functional form properties. So for example, maybe you actually think that your information is contained in pairs of particles. So maybe instead of summing over individual particles, maybe you actually think that the information is contained in pairs of particles. Okay, fine, then you build the same function, but it takes input 2 particles at a time. And then you say, no, it's not actually pairs of particles, it's only their relative distance. Okay, then you put a minus sign between them. Or maybe you say that you actually think that your problem should be Lorentz invariant, and then you could like do the full SO3, 1 structure, which is a fun thing to ask me about on Q&A, about how would you actually make sure that the function that you build is one that if I do a Lorentz transformation on these objects, you'll be guaranteed that your result is Lorentz invariant, which we can talk about later. But the point is that knowledge can be encoded in these learnable functions, and a lot of what people are doing when they're doing machine learning for fundamental physics applications is coming up with learnable functions that either have nice properties, like normalizing flows have really nice properties with respect to calculating that Jacobian determinant, or have an inductive bias built in about how you think your problem is structured. So that's all I'm going to say, by the way, about baking in knowledge. I will. You can ask me about other strategies that you might want to do. I could spend obviously a lot more time talking about it, but hopefully you're inspired to not just use off-the-shelf machine learning, but actually try to building something that you know about your problem that you might think would be relevant beyond just the training data that you start with. Okay, any questions before I get to the last ingredient? Okay. So the last ingredient is optimization algorithms. And at least the standard optimization algorithms are once again returning to our favorite classical dynamics. Only now it's not Lagrangian-based classical dynamics, nor is it, by the way, Hamiltonian-based classical dynamics, though there are actually some really interesting papers using Lagrangian and Hamiltonian dynamics in order to build new optimization strategies, and that would be also another fun thing to talk about during Q&A. But actually here, the default optimization algorithms are some variants of Newtonian dynamics. So these functions here, or any neural network, they're just kind of parameters that I can imagine moving around and trying to optimize. So we have parameters B in general, and we have a large number of them. And a standard thing to assume is that these B's are going to evolve according to some type of damped system. So we can imagine that these B's are moving around. So a neural network has 1 million parameters. So you can imagine the parameter choices as being some kind of ball moving around in a 1-million-dimensional space. That ball has momentum. Sorry, that ball has inertia rather, and maybe it's damped, and maybe it's moving around in some potential. And the standard limit that we take is we say, well, let's say this gamma is very large. And when gamma is very large, the system is highly damped and the inertia doesn't matter as much. And if we imagine replacing the classical potential with like literally the loss function, then the dynamics that I would get would be just solving, sorry, this should be a dot here, solving some, well, I don't know what is this? This is a first order differential equation. Okay, this is like so easy I can't even say the words. Okay, so the solution BI, if after one time step, is that I start off with some initial value, and then I just move by whatever my time step size is, divided by gamma, the derivative of the loss function with respect to my parameter. This coefficient out front is called the learning rate. And so if you do optimization of a highly damped system where the objects that you're trying to move around aren't balls rolling around in a potential, but machine learning parameters rolling around in a loss function, then there you go, that's the dynamics. And that's what we mean by gradient descent. And as I mentioned in last lecture, you can ask whether gradient descent makes any sense or not. Last time I made the point about gradient descent not really being maybe the most sensible thing to do if I'm thinking about covariant versus contravariant objects. But if this is the physical analog that you think is actually going to give you the best solution to your optimization problem, great, go ahead and use it. Or maybe you have some knowledge about the way that your system is built, so maybe you can actually come up with a better, more efficient optimization strategy. This is an area of research that I myself have only started to get interested in. But in terms of buzzwords you'll hear people talk about gradient descent, stochastic gradient descent, atom optimizer. And these are all different strategies, roughly speaking, coming up with equations of motion approximately that are trying to find numerical optima. And there's a whole literature on optimization, but the simplest one is, again, this classical dynamics picture, and indeed physics-motivated optimization is an interesting area of research. Okay, so that was quick. So let me just summarize where we are thus far, and then close out with an example that shows a little bit how surprisingly powerful these various ingredients can be when put together. Okay, so first, are there any questions before I move on about this? Yeah.
Actually, this very large damped system. This is something you tell us, or I don't understand, but why?
So do you agree that if I ignore this term and I solve this?
Yeah, I just don't understand why we assume that gamma is that much larger than.
Do you agree that if I were to assume that gamma is large, then this is the solution?
Yes.
And this is the solution for what gradient descent is. So gradient descent is, if I want to think about it as a physics term, is just classical dynamics in a highly damped system. Now, you can ask the question, is that a good way to optimize? So for example, so if I have a potential that looks like this, so here's my machine learning parameter, and I say I start here, and I would like to do gradient descent in a highly damped system, and I want to find the loss minimum. Okay, so I go, I'm painfully slowly getting damped down to here, and then I stop. Is that a good optimization strategy? Right? Okay, so then someone says, "Ooh, no. What you really need to do is you need to balance the inertia and this. So now I'm going to actually have some notion. It's not strictly speaking this, but colloquially, has some notion of momentum. That as this thing is moving, I'm going to it builds up speed, and then it's able to get across the barrier, right? Or maybe actually what you say is that you'd prefer to have a system that was actually energy conserving. So actually, what it does is it actually oscillates back and forth between here, right?" Maybe that's what you want to do. And you can think about for what is the physical analog, what's the physical strategy that you want to do that would correspond to a sensible optimization for your problem. Okay, Okay, I wasn't planning on doing this, but let me give you an example. Can I draw a half pipe? Okay, so let's say this is me trying to draw. Sorry, how do I do this? Okay, so Nathaniel, was a skiing accident? Is that what injured your elbow or your shoulder? Oh, bike racing. Okay, so I have my BMX bike here. I'm Nathaniel. And my goal is to get successfully to the bottom of this without hurting myself, okay? So if you go in the steepest descent direction, right, what you're going to do is you're going to oscillate back and forth, back and forth, back and forth right here, okay? Maximizing your chance for doing awesome, cool tricks and possibly busting your shoulder, okay? But you can ask, like, if I know that I want to get to here, so if you're thinking about like inflationary models, this is like some kind of hybrid inflation type situation. Like you know you want to get like down here in the most efficient way. Like somehow you would like to be able to like either ride the sidewall all the way down here if you want to get there efficiently, or maybe you first get to the minimum and then fall here. Like how do you build a dynamical system that can follow this loss landscape in a way that's efficient? And that's where some kind of physics knowledge or intuition is helpful, because we often have some understanding about how these like how these systems will evolve, and it's there's various researchers that are trying to come up with alternatives to this type of framing, but this is the default that people use. So I'm not saying it's a good thing. I'm saying that if you want to think about optimization, thinking about classical dynamics as one inspiration for how you might come up with something that's improved. Yeah. Okay, so the summary thus far. So if I want to do some kind of machine learning task, what do I need? I need training data. But, I mean, training data, this is just a fancy way of saying that what I'm doing is I'm doing Monte Carlo integration. I'm using samples to try to estimate a continuous integral. I need a loss. Okay, but really what the losses are doing, I'm literally building a Lagrangian whose optimization via the Euler-Lagrange equation corresponds to some task of interest. Okay, I have some learnable function, and the learnable function, I don't have a nice physics thing to say about it, in the sense of like, there's not a standard physics argument for how you build this learnable function, but different types of physics knowledge can inspire different types of architectures. And then at least the way that we do optimizers right now, our optimizers are essentially inspired by Newtonian mechanics. And each one of these places gives you an opportunity for innovation. And the way that you can put these ingredients together in different ways can give you surprising results. And you get to decide how much of a black box this is or not. We showed that you can put Lagrange multiplier constraints in. We can put constraints in the loss function. We can also put constraints on the learnable function. You get to decide what training data you use. You get to decide perhaps what optimizer you want to use, though I warn you, if you try to build your own optimizer and try to build it into existing machine learning frameworks, it can be quite a challenging endeavor. But I want to wrap up this lecture with just like an example that maybe shows you, and actually based on the public talk yesterday, kind of shows you how even with these very simple ingredients, surprising things can come out. Okay, so let me give you the more technical version of my epiphany, my transformation. So, I just talked about yesterday being a machine learning curmudgeon, and then I became an evangelist. What changed my mind? Okay, so here's what changed my mind. We have this P of phi, Q of phi, two samples. Let's imagine this is signal and this is background. And I just showed you that you can build a machine learning loss function, that you can get a ratio. I think I should use the word R. No, I used my notes. I'm not even consistent in my notes. Let's use R. That will, with enough training data, give you the ratio of P over Q. Okay, but come on. Like, when do you really believe that you would have absolutely pure information about signal and absolutely pure information about background? Or for the particular case that I was doing in the public talk, I would have gluons and quarks. And I just made the point that quarks and gluons, I can't make pure samples of quarks and gluons. Why? Because like the quarks and gluons are confined, and therefore there's no unambiguous definition to them. Jets are color neutral objects. Gluons carry color charge in the adjoint. Quarks carry color charge in the fundamental. And so if you have 3s and 8s of color, but your jets are made out of color neutral objects, there's like just no unambiguous way of defining these objects. And so you never have pure P and pure Q. Therefore, you can never build this ratio. Therefore, like a bunch of classification tasks that we do in fundamental physics are just kind of ill-defined. However, what if we had the following? Which maybe isn't so crazy. What if we had not pure data of signal and background, or pure data of quarks and gluons? What if we had data that was just a little bit contaminated, but not so painfully contaminated that I couldn't do any science with it? So what if I had mixtures? So you can imagine someone mixing together these two categories P and Q, and then training a machine learning classifier to learn the ratio of the mixtures. So for example, I could have a situation where I have a mixture A and a mixture B, and I use machine learning to come up with that ratio, but that mixture is not really what I wanted. What I really wanted was information about the pure categories. So I have some fraction of P plus some other fraction of Q. And so another way of saying this is that what if I had mixtures, otherwise known as corrupted training data? Could I still do reliable machine learning? Or would the answer have any scientific value? And this is essentially my complaint. My complaint was never in fundamental physics do we ever really have access to something that's pure enough where I can put unambiguous labels on things. Maybe I can grant you that I could come up with mixtures of various categories, but like I just will not grant you that I can have the pure distinctions that people assume when they're doing machine learning. And that's when I basically told my former students, to get off my lawn. Like I don't believe that the starting point of machine learning, I just don't believe it. But then you go into the machine learning literature, and then you realize that this problem is a problem that has already been solved, for which, even if I have contamination, even if I have mixtures of two categories, I have a bucket of cat images, a bucket of dog images, and then I drop them on the floor and they get mixed up. And so now I have mostly cat images and mostly dog images. Could I use that to actually extract the fundamental information, the kind of fundamental categories of cat and dog, or in this case, the fundamental categories of quark and gluon, or the fundamental categories of signal and background? And the answer is that you can demix. You can take contaminated data and separate it into its pieces. And here's how you do it. So the assumption that you'd have to make is that there are critical phase space points where but only single phase space points where only one category is present. So the most backgroundy background, or the most signally signal, or the most cat-like cat. Some region of phase space, you again only need that one point where, for example, a critical point P, this phase space point corresponds uniquely to category P, and this phase space point phi q corresponds to uniquely to category Q. You just have to assume that such a point exists. If that point were to exist, then that weight function W, evaluated at that critical phase space point where only P is active, so when only P is active, Q is gone, so then I get the ratio FA over FB. And at that critical phase space point for Q, the weight at that critical phase space point for Q is equal to 1 minus FA over 1 minus FB. And this is an assumption. It's assumption that there is at least something special about your categories. There is the most signal-like signal and the most background-like background. But it's not so crazy to assume that maybe that's true. So you do have to soak up that assumption. And then if you do that, you make the following simple plot to actually extract the fractions of this mixture. And then once you have the fractions, it's a linear algebra problem to actually get out the fundamental true underlying distributions. Okay? So let's say I were to plot the classifier that I had before, W divided by 1 plus W, and we're doing the probability of getting that. So if I had pure categories, then the probability distribution for one of the distributions would go like this, the probability for the other distribution would go like this, they would go all the way down to 0 and 1, where 0 would correspond to the most signal-like signal, 1 was the most background-like background, or vice versa. In the mixed case, because things are mixed, this classifier is limited. It can't go all the way to 0 and 1. It's actually bounded, you can show, by these endpoints. So in the mixed case, you would make the same plot. And there would be endpoints. These endpoints would correspond to, okay, once you do the manipulation of W and 1 plus W, correspond to these numbers here. One distribution would look like this. The other distribution would look like that. And to the extent to which you can resolve the endpoints of your machine learned classifier, that's the extent to which you can completely demix your samples. That is, you can deduce the mixture fractions from the corrupted classifier, which is kind of an amazing statement. Right? I can, and this is what I was saying before about in my public talk about topic modeling. Topic modeling, you can take buckets of text, find the word that's most uniquely associated with a given topic. If you can figure out the frequency at which that word appears, you can then separate out the categories. The machine learning version of that in particle physics, or more generally, is that if you have a classifier trained on corrupted data, the endpoints of the classifier tell you the degree of corruption. Under the assumption, of course, that there is some phase space point that's unique to those underlying distributions. So not only can you engineer losses to serve your purpose, not only can you make learnable functions that serve your purpose, but also by going into the machine learning literature, you can be surprised that this is like standard. And then realize, oh wait, some of the problems that we face in our field actually are ones that other people have thought about and they might even have solutions for. And this is part of my going from being a curmudgeon to an evangelist, is realizing that I can learn a lot from my colleagues who are in adjacent fields by the way that they're tackling their data sets. Okay. So any questions about that before I wrap up and we go to lunch? Yeah. Yeah.
So in case of quarks and gluons, it's sufficient to, be possible that there is an event of only quark jets and an event of only gluon jets.
Yeah.
The existence of those possibilities is enough to
Just the mere fact that there is, in fact, it doesn't even have to be only one, as long as it kind of asymptotes appropriately. That is, the ratio of quark to gluon goes. So even if there are some quarks to gluons, as long as it asymptotes to a ratio where it gets dominated by one category or the other, that's sufficient. Yeah. You can do this in multi-categories, in fact. It just that obviously the mathematics becomes a little bit more annoying to show. And then the mathematics being more annoying to show also means that numerically, it turns out that determining this endpoint from a numerical algorithm is annoying because there's like always these tails that come in here, and like actually trying to estimate it, the endpoint is a little bit tough, and trying to put error bars on that is difficult, but it is something that you can do. And there's an assumption there, but I flip things around in my head. Like I'd rather know what the assumption is and know what the implication is than to completely throw out the problem. I'd rather have a solution that, of course, is conditioned on an assumption, but then that's an assumption that you can try to refine and improve over time. Other questions? Okay, so what I've shown you here has been the basics of machine learning, and really, I really mean it when I say a lot of the stuff that's in the literature is just generalizations of the things I've shown here. And you might complain, and in fact you should complain, that the examples I'm giving are like really stupid, right? Like I keep saying cats versus dogs, 2 categories. Oh, come on. Quarks versus gluons, 2 categories. Come on. Especially in the quark versus gluon case, like I'm not even separating out uptype versus downtype, right? or their polarizations. Or signal versus background, right? Well, okay, maybe that one really is a dichotomy that we're more willing to accept as physicists. The surprise that we're going to come up with, the surprise is that what I showed here, just with P's and Q's and whatnot, very simple, that with a tiny little bit of uplift will allow you to do the entirety of frequentist statistical inference. That all it really needs are these ingredients here, and that's what I'm going to be doing tomorrow. So these simple examples are kind of an entry to the broader simulation-based inference context. And there's just one little weird trick that I need to teach you in order to see how to lift it to the simulation-based context. But I actually will spend a fair amount of time tomorrow actually talking about some statistical concepts. And for those of you who are already familiar with statistics, it will be a bit of a review. For those of you who haven't been maybe engaged with it before, my apologies in advance that frequentist statistics makes your head hurt. That is the framework that is used in my field of collider physics. I want to kind of show you how those things merge together, how you can take neural networks, learning the things of this lecture, standard traditional frequentist or classical statistics, and then push them together to actually make inferences about the universe. Okay, thank you so much, and let's all go to lunch.